Welcome everybody to the seminar of Gravitation and Mathematical Physics of Simvestab. Today, our speaker is Professor Ali Mustafazadeh from Koç University in Istanbul, Turkey. Professor Ali is the author of 3 books and more than 160 scientific articles with almost 6,000 citations if you consider publications, or 10,000 citations according to Google Scholar. His research interests are differential geometric and topological methods in theoretical physics, quantum mechanics, quantum cosmology, supersymmetry and its generalization, pseudo-Hermitian Hamiltonians, scattering theory, spectral singularities, and mathematical optics. His web page is on the chat of this meeting, and well, his talk has the title Geometric Extension of Quantum Mechanics. So please, Professor, you have more or less 1 hour.
Okay, thank you very much. It's a pleasure to give this talk. So I'll talk about this geometric extension of quantum mechanics. Here is the outline. I will begin with very basic definitions, axioms of quantum mechanics. Then I'll talk about what I mean by pseudo-Hermitian operators. I explain a difficulty with quantum mechanics when the state space becomes time dependent. Then I will review basic notions of differential geometry that I will need, that is Hermitian vector bundles, metric connections. Then I will discuss how I construct the energy operator and what this concept of energy operator for quantum systems with time-dependent Hilbert space mean, and how it relates to these geometric constructions that I will tell you about. And then I outline this global geometric extension of quantum mechanics, and I conclude with some remarks. So I start with a Hilbert space, which has this inner product. This is the kind of Hilbert space you know. And I will take a linear operator. This H is going to become the generator of time evolutions, which we call Hamiltonian. And for simplicity, I will consider just finite dimensional Hilbert spaces so that I don't get into troubles with domain of operators. A Hermitian operator means that this operator satisfies this equality for all vectors in the Hilbert space, standard definition. And a pair of Hilbert space and this Hamiltonian operator determines a quantum system in the sense that the Hilbert space determines the kinematic aspects. The state vectors are non-zero elements of the Hilbert space, and observables are Hermitian operators acting in this Hilbert space. Why Hermitian? Because there is a theorem which says that if you want expectation values of all state vectors to be real, and if you have a linear operator O that you consider its expectation values, then this linear operator must be Hermitian. Usually in quantum mechanics courses, we prove the opposite, which is easier. But this is an if and only if statement. If you want expectation values to be real, then the operator must be Hermitian. Therefore, there's no way you can use non-Hermitian operators for describing observables. The operator H, the Hamiltonian, determines the dynamic aspects of the system through the time-dependent Schrödinger equation. And the unitarity of evolution means that under this time evolution, the norm of the state vectors does not change in time. It's invariant. And again, this condition holds provided that this Hamiltonian operator be Hermitian. This is also if and only if statement. So you can't touch the hermeticity axiom in quantum mechanics despite this many advertisements that they make in saying that you can. So now I want to talk about the unitary operators which maps one Hilbert space to another Hilbert space. So there are two Hilbert spaces. They have different inner products, which I labeled by 1 and 2. And there is an operator, linear operator, which maps H1 to H2. We say this is a unitary operator if it leaves the inner product invariant. So if you pick two vectors in the first Hilbert space, map them using this U to the second Hilbert space, the inner products are the same. This is the definition of unitarity. And if you pick two pairs of Hilbert space Hamiltonians, so each of them supposed to determine one quantum system, and this theorem says that they specify the same quantum system if and only if there is a unitary operator mapping the first space to the second one, such that the Hamiltonians H2 and H1 satisfy this condition. We will return to this equation a number of times during this talk. So the reason is that this U sets a one-to-one correspondence between state vectors belonging to these two representations and observables using this equation. And these guarantee that the expectation values of this observable computed in the first representation is the same as the one you compute in the second representation. This condition that relates H2 and H1 guarantees that the solutions of the time-dependent Schrödinger equation in the first representation are mapped to the solutions in the second representation. So essentially, the time evolution is mirror image of one another, and the expectation values, which give you the physical quantities, can be computed in either. So as far as the physics is concerned, these two representations are the same. They give you the same quantum system, and you can take this and even define a quantum system or quantum systems with equivalence classes of unitary equivalent Hilbert space Hamiltonian pairs. There is a problem with regard to the energy observable, which comes from this fact. Suppose traditionally we take the Hamiltonian to also mean the energy observable. The eigenvalues of the Hamiltonian supposed to determine the energy levels. But if this is true, then you can ask, what is the energy observable in the second representation? If this is observable transformed by similarity transformations, so you get a different energy operator than the second Hamiltonian. So this leads to a problem, because you might say, well, the second Hamiltonian, the second representation is not energy observable, whereas the Hamiltonian, the first representation is. But who says which one is the first? So you see there is a problem even in defining how this energy observable is to be specified. It shouldn't be a convention if this is supposed to give us some physical information. Well, one of the observations which is important, which was made about 20 years ago, is that the axioms of quantum mechanics, this is well known obviously, do not restrict the choice of this Hilbert space. There are infinitely many Hilbert spaces. They are all isomorphic, but I mean, they are not the same. And this led to what I call pseudo-Hermitian representation of quantum mechanics. It's based on this theorem which I published about 20 years ago, 19 years ago. It says the following four statements are equivalent. The first one is the linear operator H is diagonalizable and has a real spectrum. That's if and only if this condition holds. H dagger is related to H by a similarity transformation through this eta, and this eta is a positive definite linear operator, which I call the metric operator. So metric operator means positive definite, invertible positive operator. And this equation is what I mean by pseudo-Hermiticity. This means H is pseudo-Hermitian with respect to metric operator eta. This is also equivalent to the statement 3, which says this operator that I start with is actually Hermitian if I change the inner product of my Hilbert space to this new inner product, which is defined through this metric operator. And this the fourth statement, which is equivalent to these three, is that there is an antilinear operator whose square is 1. It commutes with the Hamiltonian and has common eigenvectors with it. So best known example of such an antilinear operator is time reversal operator, and also this PT, parity time reversal operator. So when you have a Hamiltonian which commutes with PT and has the same complete set of eigenvectors, which are eigenvectors of the PT, then again the Hamiltonian is diagonalizable and its spectrum is real. Now this work on this pseudo-Hermitian operators, I was motivated by the question which is related to quantum cosmology that's called Hilbert space problem. And this led to methods to compute or construct inner product metric operators, and then to construct the Hilbert space in relativistic quantum mechanics, like the quantum mechanics of relativistic particles in first quantized theory, for bosons particularly, and for the photon. And also in quantum cosmology, you have this algebra of operators, but to determine the Hilbert space, you need to specify the inner product, which can be done using these methods. Okay, next technical and simple observation was that if you take the square root of eta, eta is positive operator, so it has a unique positive square root. I'll call it rho, but since changing the inner product on a space doesn't change the space itself, you can view rho as an operator which maps this h eta, h with the new inner product, to back to h. And then because of this simple equations, you see that when you look at rho from as an operator from h eta to h, it is actually unitary. This is the inner product in the first space. It's defined by putting eta in between the bra and ket. Eta is square of rho. You move one of the rows to the left because it's Hermitian with respect to this inner product, and you see that this says that you have calculated the inner product here and then moved phi and psi to there, and the inner product remains the same. So this is unitarity. In other words, I can define a quantum system using this Hilbert space with new inner product and this pseudo-Hermitian Hamiltonian. Or equivalently, I can use this unitary operator, rho, to introduce a new Hamiltonian, which now acts in the standard Hilbert space. And both these representations give you the same quantum system. So there's actually no need to use pseudo-Hermitian operators in a new Hilbert space. You can live in the standard quantum mechanics. Now, in 2007, it occurred to me that there is this problem. When this metric operator becomes time dependent, either the evolution generated by the Hamiltonian is not unitary, or the Hamiltonian is not observable. The reason is very simple. Being observable for the Hamiltonian means that it must be Hermitian with respect to new inner product, which means it must satisfy this pseudo-hermiticity condition. But requirement that H be unitary, that means this quantity be time independent, leads to this equation. And you compare and you see that these agree only when the second term here is 0, but eta is invertible, so that means eta should not depend on time. So when eta is time dependent, then they don't match. Either it's not observable, this is true, you have unitarity, or it is observable, then you don't have unitarity. So this was a kind of negative result, and people try to find a resolution by, for example, proposing that maybe we should change the definition of time evolution, just add terms to Schrödinger equation which kills this unwanted term. But again, this leaves the problem of what is the energy observable. When eta becomes time dependent, things require more care. Now, to set up the state for the resolution of this problem, consider a time-dependent Hilbert space, the general time-dependent Hilbert space. For example, you can imagine that you have a particle confined to move on a surface, and the surface is vibrating. Then the metric on the surface will be different at different times, but you use the metric to define the inner product through the measure. So you get a time-dependent Hilbert space. And suppose I want to write a dynamical equation for the state vectors belonging to this time-dependent Hilbert space. Now that requires the notion of time derivative. Apparently, you can start with talking about the standard definition of derivative that you remember from calculus, but this is of no use. The reason is that these two vectors which appear in the numerator, they do not belong to the same vector space. So there is no way you can make sense of what the difference is. So the best you can do is to assign to this vectors in this Hilbert space an associated vector back into the Hilbert space at time t, and then take the difference and look at this limit and call it a rate of change. This assignment is essentially what is known as a connection. And since we are interested in Hilbert spaces which have inner products, this leads to the geometry of Hermitian vector bundles. Now I'll try to outline very fast what this construction of Hermitian vector bundle is. So a vector bundle is a manifold. It comes with another manifold, which is called the base manifold. There is a continuous function, which is called the projection from this E, the total space, to the base space. If you pick any point in the manifold, which I usually use R to denote, there is a piece of the big space which is projected on this point. All of these look alike, and there are vector spaces of the same dimension. These are called fibers of the bundle. This is the fiber over the point R. And all of them are isomorphic to, I consider, complex vector bundles, because all of them have the same dimension, capital N. They are isomorphic as vector spaces to Cn. And V stands for Cn throughout this lecture. Now you can look at two patches, two coordinate patches, and try to look at the inverse image of points on each patch. One requirement of vector bundle is that there are these patches, and the inverse image of patches under these projection maps are just cross products, trivial cross product of the set in the base manifold times the Cn, which is called a typical fiber. This is a homeomorphism, phi alphas, which you can write if you pick one point in the fiber over R here, which I call V. This will map it to a point in O alpha, which is its projection down here, and a point in the typical fiber, which I call Z here. Why are these maps? These maps are vector space isomorphisms. So fibers are isomorphic to V, and this gives a particular isomorphism between these two bundles, these two vector spaces. And you can also do the same in a second patch which overlaps. So the same construction will give you a new set of phi beta R's, and then you can compose these phi alpha and phi beta R's to go from one copy of the typical fiber to the other copy. And these are called transition functions. The use of these transition functions is that now you can look at the part of the bundle which lies over the union of O alpha and O beta as a pair of O alpha cross V and O beta cross V. And in the intersection, you have to glue these 2 points coming from 2 cross products, and these are the gluing maps. So once you have transition functions, you can just paste together this local patches and construct your bundle space. Now let's look at one fiber over R. Remember, there are these isomorphisms to the typical fiber. Typical fiber is C to the N, and suppose this E1, E2, En are the standard bases is Cn. Because phi alpha is an isomorphism, I can use it to construct a basis in the fiber over R. These are I denote by psi1, psi2, psi_n. Everything happens at one point R, so everything depends on that. This way you get a basis over each of the fibers. Now, suppose you have a mapping which maps base manifold to the vector bundle. These are called global sections. At each value of R, it will give you a point in the fiber over R that you can expand in the spaces. So you get certain components which depend on R. So you get these component functions, capital psi n, which take points in the patch you have started with to complex numbers, because these are complex numbers. You can arrange these into a column vector, and this defines you a bunch of so-called vector fields over the local patches. In particle physics, these are the matter fields. Now, let's take a curve in the base manifold M. It's a parameterized curve. CT is the point in one of these patches. I use RT to mean that I use some coordinates. I have coordinate patches in or coordinates, local coordinates in O alpha, which collectively I call R sub t. And then as I move along the curve, R changes in time, so the fiber over this point will be a moving fiber in the bundle space. Now let me take a point in the fiber over at time t, and the parameter of the curve I identify with time. But I can represent this using this local coordinates. If I change the value of time by a small amount, I move to the next nearby fiber. And again, there I have the basis vectors. Again, there should be some coordinates, which will depend on t plus epsilon. And remember, I wanted to assign a vector at vt to this vector, which is at vt plus epsilon. So what do? I just take these coordinates and define a vector in vt. So how do I define this coordinate? I use this rule. So I say this psi sub n at t plus epsilon should be a linear function of psi, and it should be first order in epsilon because I'm going to take epsilon to 0. And here, you remember this boldface psi is a column vector. So these are some n by n matrices. And this is the time derivative of coordinates in the local coordinate. This gives you the curve. And this A alphas, which are n by n matrices, are nothing but what's called the local connection components. You can use it to determine this, to define connection 1 forms. And these are n by n matrices. And the connection on such a vector bundle is a local consistent assignment of these local connection 1 forms to all patches of your bundle. Now, with this construction, you can also write this condition in terms of a compressed notation. This dt is defined like this, and it's called covariant time derivative. These are well-known quantities. Now let's take, we have a curve in the base manifold, and I will try to define a curve in the full bundle space by identifying these psi n's by the solution of this differential equation. This first order differential equation, if you have a initial condition, you can integrate it, and this gives you a curve in the total bundle space. This is called the horizontal lift of the curve in the base manifold, and this is the picture. All of this is local. It happens in one local patch, and if you take the initial condition of your differential equation and you generate this curve is said to be obtained by parallel transportation of the initial vector in the initial fiber. So this is the notion of parallel transportation in vector bundles. Now, a Hermitian vector bundle is a vector bundle where each of the fibers have an inner product, and these are smoothly defined. So each of the vectors, fibers, come with an inner product, which again can depend on R, and they do depend on R. So now remember, I had used the basis vectors in Cn to get these basis vectors in the fiber over R, and now I can also talk about their length and their angle. In principle, these phi alphas are isomorphisms, but they are not unitary maps. So there's no reason why, for example, the angles should be the same. Now, a metric connection is a connection such that if you take a pair of vectors and parallelly transport them, the inner product remains the same. Oops. So this is the definition of a metric compatible connection. You have a connection which you can use to generate these parallel transportations, and you can also calculate the inner product. The compatibility means that the inner product is invariant under parallel transportation. Okay. Next, I will take these basis vectors in my fiber over R. There are n of them, and this inner product gives you an n by n matrix, complex matrix. I will take this complex matrix and use it to define, as usual, a linear operator acting on Cn, right? Just multiplication. So the elements of Cn are column vectors. This is n by n vector, the n by n matrix. So this gives you a linear operator. And this happens to be a metric operator. It happens to be a positive definite operator, which you can use to define an inner product on Cn. Similarly, I had these components of the local connection one form. They are n by n. And I also introduce a new n by n matrix, H sub A, using this ANs by this combination. So this matrices I can also use to define linear operators in Cn. And what happens is that this condition of parallel transportation can be written as a time-dependent Schrödinger equation with this Hamiltonian. This is a matrix Hamiltonian. And if your connection is a metric connection, then it satisfies this condition, which says if I use this eta to define an inner product on the typical fiber, then this Hamiltonian generates a unitary time evolution. So going back to these notions of pseudo-Hermitian quantum mechanics, I now have a new inner product on Cn, and with this inner product, this parallel transportation, which defines a time evolution, becomes unitary. Well, if you look at this time evolution, which is geometric, it just gives you parallel transportations, you discover that you have in the Schrödinger equation a time derivative, and also in the definition of the Hamiltonian, you have a time derivative. That says that this evolution is time reparametrization invariant. Scaling time doesn't change the outcome of the evolution. This is purely geometric, as it's obvious from the construction evolution. Now, to connect all this to physics, I will consider the components, the coordinates of the points on the curve in the Bayes manifold as certain parameters that enter the definition of the Hilbert space, which is this space. And the choice of the curve determines how these parameters change in time. And the choice of the connection determines this Hamiltonian, which defines parallel transportations. They lead to horizontal lifts. Therefore, I call this evolution a horizontal evolution. Next, I will take the other extreme. Suppose I am frozen in time, so I am at one point in the Bayes manifold, and I want to define a time evolution in this Hilbert space. Then eta is just a constant, it's a constant Hilbert space, and then it has some inner product, and I want to generate the time evolution using the time-dependent Schrödinger equation. The Hamiltonian will be a matrix, which is pseudo-Hermitian, with eta being my metric operator. Well, I can use these maps, which take points in the typical fiber to points on the fiber over R, and under this isomorphism, then I will get an evolution of time happening at the fiber over R. So these are vectors change in time, but they don't leave the fiber. So this kind of evolutions I will call vertical evolutions because they happen at one fixed fiber of the bundle. Now I propose that in general, we should have Hamiltonians that is a combination of horizontal evolutions and vertical evolutions. So they are defined in terms of this HA, which gives you the parallel transportation, plus this kind of Hamiltonians, which give you the vertical evolutions. Now, does such a definition give you a unitary evolution in the typical fiber? Well, by definition, A being metric compatible gives you this equation. The fact that HE defines unitary evolutions along vertically gives you this equation. When you add them up, you can show that this Hamiltonian, this red Hamiltonian, satisfy the same condition which is required for the evolution to be unitary. So this is unitary, the general unitary evolution in the Hilbert space H sub eta. Remember, H sub eta is the typical fiber with a new inner product given by this eta. Now, the proposal is that this HE that gives the vertical evolutions is the energy observable. So the Hamiltonian is the energy observable, HE, plus this geometric Hamiltonian, which comes from the connection. One can actually obtain a characterization of metric compatible connections. You can show that every metric compatible connection has this canonical piece, which is given by the metric, and plus a pseudo-Hermitian map matrix valued one form, gamma, and this also satisfies not pseudo-Hermiticity, but an extra minus sign, which is called pseudo-anti-Hermitian. And then you can write the Hamiltonian in terms of the energy observable, which is pseudo-Hermitian. This piece comes from 2a0 and omega. This is the contribution when A is just omega. So it's pseudo-Hermitian, and the rest is just canonical part, which is pseudo-anti-Hermitian. So this is essentially the picture. So we have a base manifold here. There's a point above which there's this fiber. We moved from fiber over R to the typical fiber. We put an inner product on it to make this phi a unitary operator. And then we could also go to the standard Euclidean inner product by the square root of eta. Remember, this was a unitary mapping which takes this representation to this representation. So all what I said admits a simple quantum mechanical representation with standard Euclidean inner product on Cn. So you use this rho, you can define the Hamiltonian in acting in the standard n-dimensional n-level system Hilbert space. Each of these three counterparts have its Hermitian counterparts, and they are defined by these formulas. The formulas are not important, but the whole point is that you're back to quantum mechanics. The only difference is that now I know that the Hamiltonian, the Hermitian Hamiltonian, is not the energy operator. One piece of it is energy operator. The rest is a geometric component which should be there. So locally, this is all standard quantum mechanics. But this admits a global extension, which is what I call geometric extension of quantum mechanics. To give you the axioms of this extension, I need one more mathematical object. So I use U V of R to denote the vector space of Hermitian operators acting on the fiber over R. Remember, fiber over R is an n-dimensional, finite dimension complex vector space. So this is the set of n by n Hermitian operators or matrices acting on this. And I use these as the fibers of a vector bundle over the same base space. This is a real vector bundle because the vector space of Hermitian operators is not a complex vector space, it's a real vector space. You multiply a Hermitian operator by a complex number, it's no longer Hermitian. So the typical fibers are these. The fibers are these. The typical fiber is the Hermitian n by n matrices, which you can identify with the Lie algebra of the group UN. That's little un. That's why I use this little u. And then you can construct this transition functions. I don't have time to explain why you define it this way, because it works. This is very natural. So I don't want to go through the details of these construction. It's all in the paper. Anyway, so what the point is that there is this Hermitian vector bundle whose points are Hermitian operators. Now, the axioms of this extended quantum mechanics is as follows. A quantum system is described by 4 ingredients. First, you have this Hermitian vector bundle E, which I constructed. It has a base manifold M. On this vector bundle, there should be a local connection 1. The local connection 1 forms, that's a metric connection, which gives you the local connection in patches. Then you have to have a global section of this new real vector bundle. So for each point in the base manifold, you should be a well-defined unitary operator acting on the fibers of. Finally, you need a curve in the base manifold, which determines how your parameters change in time. Now, vectors at time t are points on the fiber VCT. CT is a point in the base manifold. On top of it, there's a fiber, and the state vector at time t is a non-zero element of that fiber over CT. The observables are global sections of this bundle UE. So this is an assignment to each point in the base manifold and a Hermitian operator acting on the space of state vector at time t. The measurement axiom is given by von Neumann's projection axiom as follows. So at time t, you want to do a measurement. You have to have a state vector which belongs to this fiber, and you have to have an observable. The observable omega is a global section. You evaluate it at this point. So you get a Hermitian operator acting in V, and that VCT, the fiber over CT, has an inner product. So you can use to define the expectation values. So you don't run into any trouble with the projection axiom of quantum mechanics. It extends to this global picture. The third ingredient, a specific global section of this bundle, gives you the time evolution. So the ingredient 3 is available. You identify it with the energy observable, and the time evolution is given by this formula. This is covariant time derivative in a global sense. This is the energy observable evaluated at the point of the base manifold CT. It is determined by this connection. So 2 also enters the game. Now, if you again go back to one local patch or alpha, you can use this isomorphisms to get a local representation of this global Schrödinger equation to get local coordinates of evolving states, either in this representation or this Hermitian representation. What happens is that once you have the connection, you have the local connection bound forms, and you can show that this, if you sandwich this global covariant time derivative, you get the local covariant time derivatives, which has this form. And then again, by sandwiching this phi's, using this phi to sandwich this observable energy observable, you get the local representation of it, which is an n by n matrix. And then the global Schrödinger equation reduces to a Schrödinger equation for the local coordinates of psi t's. Just by calculation, you see that this piece, the covariant time derivative, becomes this for the coordinates, and the right-hand side, using this, it gives you HE. Now you multiply this I with this I, get a minus sign, you move it to the right-hand side, you go back to where I started with. You get the Schrödinger equation with the Hamiltonian, which has 2 pieces. This piece comes from this observable, which I called energy, and this piece comes from the connection, which is the geometric piece. So the bad thing about all this study was that it's very difficult to come up with exactly solvable toy models to study what these quantities are. The simplest toy model which I could compute all the ingredients was a 2-level system based on a sphere. I wanted the bundle to have non-trivial topology, which restricts the choice of the base manifold. The simplest is S2, and obviously 2-level is simpler. N is equal to 2, the simpler possible case. And then I got the sphere and put 2 patches, which contains the North Pole and the South Pole, and try to give the most general metric compatible connections to compute them like this. And all these calculations are given in this paper. It's a lengthy calculation, took like 8 pages of the paper to write down the end results. Well, a general introduction to this geometric extension of quantum mechanics is given in this paper, where I also describe how the Heisenberg picture of dynamics works in this fiber bundle setting. So let me conclude by saying that the resolution of the problem with identification of the energy operator for a system with a time-dependent state space requires a vector bundle formulation of quantum mechanics. This leads to a proposal for a geometric extension of quantum mechanics in local patches of the fiber bundle. It gives precisely the quantum mechanics that we know, but it has a global aspect. The time evolution is given by a covariant global Schrödinger equation, and energy observable appears in its right-hand side. Locally, it gives the Schrödinger equation we know, but it splits the Hamiltonian in 2 pieces. One geometric piece, one energy observable piece. You can go back to the standard notion when the Hilbert space, just the Euclidean space Cn, then the Hamiltonian there also splits into 2 pieces. The energy operator plus a geometric piece. Well, when the Hamiltonian is not time dependent, it may happen that this HA is 0 and you don't see it, but it's there. This is like a gauge transformation. Okay, an open problem, which I have no clue, is the following. You see, locally it's quantum mechanics that we know. Globally it's not, because these bundles can have non-trivial topology. But I have no idea what this topological, non-trivial topology of this bundle means physically. Well, here are again the 2 basic references on the subject, and with that I complete my talk, and I thank you for listening.
Thank you so much. We have time for questions, so if you have questions, please raise your hand. Okay, we have a question from Ivan Alejandro Bocanegra, please.
Yes, thanks. Can you hear me?
Yes.
Yes, we can hear you.
Yes, I have what may be a very basic question. At the very beginning, you redefine the inner product.
Yes.
You add in one of the entries this eta.
Right.
My question is very simple. What happened with the probabilistic interpretation of the usual inner product?
Oh, it's there. So let me try to find the correct. Can you see this?
Yes.
Okay, so the way I define the expectation values, it's the way you calculate the probabilities, right? If you take the observable to be a projection operator, then that will be giving you the expectation value of that probability. That's the transition. So you can calculate the probabilities exactly as you know in quantum mechanics. The point is that interpretation, the probabilistic interpretation, has to do with the measurement, and measurements appear at one point at time. So when you are at a single point in time, this is exactly like ordinary quantum mechanics.
Okay, so what happens when you introduce this time dependence?
I can't hear you.
Yes, I said that. Then what happens when you introduce the time variable?
Yeah. Well, I described how the evolution is, but you see, you're asking about probabilistic interpretation. Right. So you calculate the probabilities as a point at time, right? So you have to fix time, and ask what is the probability of measuring this at this time. And in that case, this is the formula for the expectation value. And if you make the observable into a projection operator, that will give you the probability amplitude. You square, you get the probability. So the time evolution and the measurement axioms do not interfere. That's the point.
Oh, okay. Thank you very much, Professor.
Welcome.
Okay, thank you. We have a question now from Ricardo Capovilla.
Thank you for the very, very nice talk. I would have never suspected that the Hamiltonian really was a connection. Which brings me to my first question. If it's a connection, does it have a curvature, field strength?
Yes. So
you're turning quantum mechanics into a gauge theory, basically.
exactly. But this is a little more than that, because the Hamiltonian has two pieces. Well, maybe I should have it somewhere. Yeah, here. So the Hamiltonian has two pieces. One part of it is geometric, so it comes from a connection. But the other part, which is the energy observable, is added to it.
Mm-hmm.
So if the energy is zero, no energy, that's completely geometrical. And then that's just a parallel transportation.
Well, there are important Hamiltonians that are actually zero, like the one for general relativity.
Well, that's a little different, yes.
Anyway.
This is standard non-relativistic quantum mechanics.
I know, but the structure is definitely very, very interesting. And thank you for your talk.
You're welcome.
Okay, now we have a question from Piotr Kielanovsky.
Okay, I would like to ask at the very beginning about the eta operator. You say it's positive definite.
Yes.
There must be some mathematical proof, but for matrices, it seems that you know, if you have a diagonal matrix with real diagonals, and then take any matrix, say complex, on the previous page, on the previous, this.
Let's see, I have it here, yeah.
Yeah, okay. So it must be, so what is this, why is it eta positive definite?
Because you want to have an inner product which has this axioms of inner product, right? The norm you want to be non-negative. And you want
does it have to be or you just choose it to be?
No, this is necessary. Every inner product on n-dimensional complex space can be obtained from the Euclidean inner product in this way.
Because, well, I like this relation, but I was just thinking about, well, I would like to have to see the proof. Because you see, in my opinion, this relation that eta is positive definite is really, without that, you wouldn't have a whole theory.
That's right. It must be inner positive definite. Otherwise, the inner product will not be positive definite inner product.
How do you prove it? I mean, in a few words.
Yeah, actually, I kind of did it through my construction. You see, I had this basis vectors, remember? And I took the inner product of basis vectors. Well, maybe I should find it for you.
I mean, I can look for it, but yeah. the fact that it is positive definite, for me, it is very, I mean, I wouldn't expect it to be. So it's, and since it's so crucial, that's why I got really curious.
Yeah, you see in this equation here, I had this basis vectors, right? Psi n's are basis vectors. And I took the inner products, right? So that will give me a matrix. You can show that this matrix is positive definite. And from there, you can go back and define it like that.
I would have to think about it.
Okay.
But okay, okay. Thank you very much.
Welcome.
Okay, thank you. Now we have a question from David Fernandez.
Hi, Ali. Very good talk. Thank you very much. In general, the treatment is quite general, but I would like to see what happens with these particular examples. For instance, and not very complicated. What happens if you just have a standard Hermitian spin subject to a constant magnetic field? In that case, this Hamiltonian, which is stationary and not time dependent, cannot split, or there is this geometric and this dynamical part, or directly is the dynamical part in the time independent case.
So when it's time independent, the point is that this geometric part is equal to 0. So you don't see it.
Okay.
The geometric part becomes important when the Hilbert space becomes time dependent.
Okay.
When everything is stationary, you just have, it's like choosing one gauge, which is at one point is 0.
So this means that in the time independent case, it is completely dynamic or something like this. It's non-geometric in some sense, no?
Yes. Yes.
Okay.
That's
Well, the next example is the standard one. Now, you start to rotate this magnetic field. Of course, now it's time independent. And of course, you can find the exact solution, going to the rotating frame, etc. So in that case, I guess that is not so simple, but perhaps it is. It will be a classification, more or less. What will be the part, the geometric part, and the dynamical part, or there is no?
Yes. Actually, you see, it's a good example. You take this rotating magnetic field Hamiltonian. Right? You can map it by unitary transformations, which does its rotation for you in a rotated frame. In the rotated frame, the Hamiltonian is not just similarity transformation of your initial Hamiltonian, right? You have this extra piece. That extra piece is the geometric piece.
Okay. This is the non-inertial, I will say, the non-inertial term in the rotating frame.
Right.
Okay.
Right.
Yeah. Okay, that's for me explains a lot. Okay, it's very good, eh? So it was very good talk. Thank you, Ali.
Awesome.
Now we have a question from Cesar Muro.
Very nice talk. Thank you, Professor. One question is if then the parallel transport leads in your patches leads to a Schrödinger equation, and all the formalisms is made in state vectors. My question is if these formalisms can be extended when you work with density matrix.
Well, I think all of this can go through. See, locally, it's ordinary quantum mechanics. So when you talk about density matrices, rather than state vectors, you work with a kind of observables, right?
Okay.
So what happens is that you will get a picture of this, like I had introduced this second observable, the space of observables, this bundle UE. You see, the density matrices are going to belong there. They will be global sections of this UE. So you can have you can extend it to there, but I haven't done.
Okay, because then you know, well, in local coordinates, the page, well, the parallel transport leads to a Schrodinger equation, and the evolution and with density matrix is the von Neumann equation.
Right.
So then you have to weigh the some kind of von Neumann equation for the parallel transport or in local coordinates.
Yes. That will give you the von Neumann type equation in this bundle. This U bundle.
Okay, and another question, you mentioned Hamiltonian in some part of the talk that Hamiltonian time independent, a time independent Hamiltonian, and then you multiply by the metric eta, and then you say that this Hamiltonian evolves in time, but I don't have clear how was that Hamiltonian started to evolve in time. If you mentioned at the beginning that just there, and in vertical, you apply and if you apply and you can say something about a time evolution operator.
Yes. What I meant was by freezing things. I mean, you can imagine. You see this. We had a curve in the Bayes manifold, right? This latency t. Now suppose that's a parameterized curve, so it takes some interval of time to points on the local coordinate in M, right? Now suppose that's a constant function that maps all times at one point.
Okay, yes.
So then time evolves, but the point doesn't move on the curve.
Doesn't move.
Yes. So you are at one point in your Bayes manifold, and therefore you are at the fiber over that point. Time still moves, but the curve doesn't move.
Oh, yeah, I understand. Okay. And the last fast question is that related with the first question, these translations to manifolds and a covariant derivative remembers a lot of Riemann manifolds, and you define a covariant derivative. You can define something like a Riemann tensor or something like that, and if how the curvature can be measured.
So Riemannian geometry is actually a special case of geometry of vector bundles. It's not different. It's the geometry of the tangent bundle. So you can define the curvature for the connection. Exactly like the field tensor, electromagnetic Maxwell tensor, you define it from the vector potential, right? So there is a notion of curvature on the vector bundle. And these metric compatible connections that I'm using, they do have curvatures. They are not flat.
Oh, yes.
So you can actually calculate them. But I didn't do it because I don't know what they are good for.
Yes, that is the meaning of that. But it maybe have it has a meaning, an interesting meaning. You know how calculate classical expectations now. Maybe there will be something more. I don't know.
Yeah.
Well, is that my questions? Thank you.
Welcome.
Okay. Thank you. Is there any other question?
Well, it was basically my question, and I think topological non-trivial bundles will involve figuring out the field strength of the connection, because that's basically an abstraction.
That's right. But the point is that even if they are topologically trivial, again, they can have curvature.
Yeah.
Yeah, so the notion of curvature is there.
And,
whether it's
the relevant geometry is Cartan, really, not so much Riemann. These are Cartan geometries.
Right. It is geometry of the vector bundle, not the Riemannian manifold. No, the Riemannian space has, I mean, the geometry of that is not relevant, and I didn't define even it.
No. Thanks again.
You're welcome.
Well, I have one question.
Sure.
Well, here you explained how to work when you have a finite Hilbert space. The generalization to a separable Hilbert space is easy, or it's going to be complicated?
Well, once you go to infinite dimensional Hilbert spaces, you have this theory of Hilbert bundles. Now, if it's a separable infinite dimension Hilbert space, things become actually, in one sense, simpler. You can prove that infinite dimensional separable Hilbert bundles are all trivial.
Okay.
So they are topologically trivial, but as I mentioned, they can have non-trivial connections and curvatures. But then it's infinite dimensional, so these become not matrices, but operators.
Yes.
So again, I didn't have any good examples to work on. So
okay.
I don't know many things about what happens and what can be done in infinite dimensions, but I know at least it is trivial, so shouldn't give you something very strange.
Okay, thank you. We have another question from Adrián Escobar.
Yes, no, thank you, Professor Ali. Very nice talk.
Sure.
My question is related with this formalisms of the path integral in quantum mechanics. So you have this key point to split the Hamiltonian into parts, the geometric and then the observable. What do you think will happen if we try to start this, but at the level of the path integral?
Well, you see, this is a finite dimensional Hilbert space setting.
Yes,
so,
yes. No, then we extend to, yes.
Yeah, if you extend to infinite dimensions, then apparently that you should be able to do that. But the things are more difficult because, you see, I had this bundle of Hermitian operators. In infinite dimensions, these bundles are very complicated because you know that Hermitian operators don't have full domain, so they have different domains. So it's very difficult to work with them. People, for example, concentrate on the unitary operators, the exponential of the Hermitian operators, and then work there, which is feasible because then the domain is everything. But I haven't done anything in that regard, and I don't know, because path integration, you have to define the position and momentum operators and try to set up your path integral either in the Hamiltonian formalism or Lagrangian. But I don't know how that's been done in this infinite dimensional case.
Sorry, intervene. I thought the same question. And my idea is that probably it will affect the measure in the path integral. And it would...
Yes, actually, I wrote a paper in, I don't know, 2007 or 8, where I showed that in the setting, which is everything is time independent, so you don't need to go to bundles. In standard quantum mechanics, when you have, you define the Hilbert space using this non-trivial, non-standard metrics, the choice of the metric will enter into the measure of the path integral.
Yes, that's what I expected.
Yes, yes. It's a physical review D paper of, I don't remember the date, 2007 or 8.
No, thank you very much. Very, very interesting.
You're welcome.
Thank you. We have one last question from David Bermudez.
Hi, thank you, Alonso. So, well, I have two short questions, hopefully, but maybe if you can help me with the first one, it will be enough. I heard a talk that you gave 10 years ago now, and that talk you were trying to convince some of the community that works in quantum mechanics on the notion of basically what you told us of pseudo-Hermitian Pseudo-hermicity was the true notion in opposite to PT symmetry. And that basically there's no, or like you can define these classes of equivalence between the Hamiltonians, and like you can, what you learn from one, you can learn from the other. But
yes,
in that moment, I remember thinking that kind of like the community was trying to ignore you, because the
yes,
easy thing to do was to do PT things. And
right.
I believe that that trend continued, even though from what I gather, like the true notion, I agree with you basically on that. The true notion is the pseudo-hermicity.
Yes.
What changed during that time?
Well, the point is that the community of PT people, for them, this PT is like a religion. So they want to push it to at any expense, ignoring what is right. And what they did was to approach experimentalists and this optics people. And optics people, you know, they have very limited mathematical background. So they essentially accept whatever the other guys say. But the point is that, well, in classical optics, yes, PT has some applications. Actually, to be honest, there's just one important application that I know, and that is when you're talking about this unidirectionally invisible setups, you can show that the definition of unidirectional invisibility gives you a boundary conditions, which is actually PT symmetry. So when you have PT symmetry in a setup, an optical setup, it's very easy to find the configurations of the setup, which makes it unidirectionally invisible. And they found some practical applications of models which were PT symmetric. But this did not mean that these applications could not be done without PT symmetry. I actually wrote papers in optics where I showed that, for example, they claim that you can have this PT lasers which act on both laser and absorber at the same time, but that's not just the property of PT symmetry. You can have non-PT symmetric setups which has that property. So it's, I don't understand really why people are insisting. It has to do with their ego mostly. So I don't know, except this unidirectional invisibility where PT plays a simple role. I don't know very basic fundamental reason why one has to stick with PT. And furthermore, it's not sufficient. I mean, the initial papers written by Bender, some of them are not correct. I mean, I tried to correct some of them, and then we got into personal conflict, so I stopped.
Okay.
Thank you very much. Thank you very much.
Okay. Well, I think it's late for everybody. So I will ask you to turn on your camera and your microphone to thank Professor Ali for his talk. Thank you very much.
Thank you.
Thank you. Thank you.
Okay, thank you very much and good luck.
Thank you.
Thank you. It was a pleasure to see you, Ali, again.
See you again.
Yeah. Goodbye.
Okay. See you later.
All right. Bye.